Have you ever wondered why honey flows so slowly compared to water, or why some liquids like ketchup seem to change their thickness when you shake them? The answer lies in a fascinating property of fluids called viscosity. Viscosity is the resistance of a fluid to flow. It's a measure of how thick or sticky a fluid is. Think of it this way. Imagine trying to stir a spoon through a bowl of honey and a bowl of water. The honey, being more viscous, will resist the spoon's movement more than the water. This resistance is what we call viscosity. It's a fundamental property that affects everything from the way liquids pour to how they interact with surfaces. Viscosity is all around us, influencing countless everyday phenomena, from the smooth flow of ink in our pens to the lubrication of engines in our cars. Understanding viscosity is crucial in both science and engineering. In this exploration of viscosity, we'll delve into the different types of fluids, their unique characteristics, and the profound impact viscosity has on our world. Viscosity is a measure of a fluid's internal friction. This friction arises from the interactions between the molecules within the fluid. In simple terms, it's the stickiness between the fluid's molecules as they move past each other. The higher the viscosity, the stronger these intermolecular forces, and the more resistant the fluid is to flow. We can visualize viscosity by imagining a stack of playing cards. If the cards are smooth and slide easily over each other, the stack represents a low viscosity fluid. Conversely, if the cards are rough or sticky, making it difficult to slide them, the stack represents a high viscosity fluid. Viscosity is typically measured in units called Pascal seconds, PS, or millipascal seconds, mmPas. For reference, water at room temperature has a viscosity of about 1 MPas, while honey has a viscosity of several thousand MPas. This significant difference in viscosity explains why honey flows much more slowly than water. Fluids are broadly classified into two categories: Newtonian and non-Newtonian. Newtonian fluids, named after Sir Isaac Newton, exhibit a constant viscosity regardless of the shear stress applied to them. This means that their flow behavior remains consistent no matter how fast they are stirred, poured, or subjected to pressure changes. Water is a classic example of a Newtonian fluid. Whether you pour it gently from a glass or stir it vigorously, its viscosity remains the same. Other examples of Newtonian fluids include oil, gasoline, and air. The predictable nature of Newtonian fluids makes them easier to model and analyze in engineering and scientific applications. Understanding the behavior of Newtonian fluids is crucial in various fields. For instance, in civil engineering, the design of pipelines and dams relies heavily on accurate calculations of water flow rates, which are directly influenced by viscosity. Similarly, in the automotive industry, the viscosity of engine oil is carefully controlled to ensure optimal engine performance and lubrication. In contrast to their Newtonian counterparts, non-Newtonian fluids exhibit a more complex behavior. Their viscosity can change depending on the applied shear stress or force. This means that their flow behavior is not constant and can be influenced by factors like stirring, shaking, or pressure changes. One type of non-Newtonian fluid is shear thinning fluids, also known as pseudoplastics. These fluids become less viscous when subjected to shear stress. Ketchup is a prime example. When you shake a ketchup bottle, you're applying shear stress, which causes the ketchup to thin and flow more easily. Other examples of shear thinning fluids include paint, blood, and whipped cream. Another intriguing type is shear thickening fluids, also known as dilatants. These fluids, unlike shear thinning fluids, become more viscous when subjected to shear stress. A mixture of cornstarch and water, often called oobleck, is a classic example. When you apply pressure to oobleck, it transitions from a liquid-like state to a solid-like state, becoming more resistant to flow. This unique property arises from the particles within the fluid jamming together under stress. Viscosity plays a crucial role in countless everyday applications, often without us even realizing it. In the kitchen, the viscosity of cooking oil affects how well it coats food and transfers heat during cooking. Thicker oils, like olive oil, tend to cling to food better, while thinner oils, like vegetable oil, are better suited for high heat cooking. In the automotive industry, engine oil's viscosity is critical for proper engine lubrication and performance. The oil must be thin enough to flow freely at low temperatures, ensuring easy engine startup, yet thick enough to provide adequate lubrication at high temperatures and under stress. The pharmaceutical industry also relies heavily on viscosity control. Medications in liquid form, such as syrups and suspensions, must have a specific viscosity to ensure accurate dosing and ease of swallowing. Similarly, in the cosmetics industry, the viscosity of lotions, creams, and shampoos is carefully adjusted to achieve the desired texture and spreadability. Viscosity is not just confined to the realm of human-made products. It plays a fundamental role in the natural world as well. The viscosity of blood, for example, is crucial for maintaining healthy blood flow throughout the body. Blood's viscosity is carefully regulated to allow it to flow smoothly through even the tiniest capillaries, while carrying oxygen and nutrients to cells. Volcanic eruptions provide another dramatic example of viscosity in action. The viscosity of lava, molten rock that erupts from volcanoes, determines the nature and explosiveness of volcanic eruptions. Low viscosity lava, like that found in Hawaiian volcanoes, flows easily and produces relatively gentle eruptions. In contrast, high viscosity lava, like that found in stratovolcanoes, is thick and sticky, leading to more explosive and dangerous eruptions. The flow of glaciers, the movement of tectonic plates, and the formation of sedimentary rocks are just a few examples of how viscosity shapes our planet's geological processes over vast timescales. Understanding viscosity helps us decipher Earth's history and predict future geological events. From manufacturing processes to cutting-edge technologies, viscosity plays a pivotal role in shaping our technological advancements. In the production of plastics, for instance, controlling the viscosity of molten polymers is crucial for achieving the desired shape, strength, and flexibility of the final product. Viscosity is also essential in the world of 3D printing. The precise deposition of materials, layer by layer, relies on carefully controlling the viscosity of the printing material, whether it's molten plastic, liquid resin, or even concrete. In microfluidics, a field that deals with manipulating tiny volumes of fluids, viscosity becomes even more critical. Researchers are developing innovative devices, such as lab-on-a-chip systems and microfluidic sensors, that rely on precise control of fluid flow at microscopic scales. These advancements have the potential to revolutionize healthcare, diagnostics, and drug delivery systems. The effects of viscosity extend even to global climate change. As temperatures rise due to global warming, the viscosity of seawater decreases. This seemingly subtle change can have far-reaching consequences for ocean currents, marine ecosystems, and even weather patterns. The decreased viscosity of warmer seawater can alter the ocean's ability to absorb and transport heat, potentially influencing regional and global climate patterns. Additionally, changes in seawater viscosity can affect the movement and distribution of marine organisms, impacting food webs and overall ocean health. Understanding the complex interplay between viscosity, temperature, and ocean dynamics is crucial for predicting the long-term effects of climate change on our planet. By studying these intricate relationships, scientists can develop more accurate climate models and inform policies aimed at mitigating the impacts of global warming. While we've explored the importance of viscosity in everyday fluids, the world of physics offers even more extreme examples. At extremely low temperatures, some fluids exhibit a remarkable phenomenon known as superfluidity. Superfluids have zero viscosity, meaning they can flow without any resistance whatsoever. Helium-4, when cooled to near absolute zero, transforms into a superfluid. It can flow effortlessly through the tiniest cracks and even climb the walls of containers, defying gravity. This bizarre behavior arises from quantum mechanical effects that govern the behavior of matter at such low temperatures. On the other end of the spectrum, we have extremely viscous materials, some of which behave more like solids than liquids. Pitch, a substance derived from tar, is a classic example. It's so viscous that it appears solid at room temperature. However, over very long periods, it flows incredibly slowly, with a single drop taking decades to fall. From the flow of blood in our veins to the eruption of volcanoes, viscosity is an unseen force that shapes our world in countless ways. Understanding viscosity is not just an academic exercise, It's essential for advancements in engineering, medicine, manufacturing, and our understanding of the natural world. As we've explored, viscosity influences the behavior of fluids, from the simple flow of water to the complex dynamics of non-Newtonian fluids. Its applications are vast and varied, impacting everything from the design of engines to the development of life-saving medications. As we continue to unravel the mysteries of viscosity, we gain a deeper appreciation for the intricate workings of our universe. From the smallest atom to the largest galaxy, viscosity plays a fundamental role in shaping the world around us, reminding us that even the most seemingly simple properties can have profound and far-reaching consequences.